In our last video, we talked about adding two vectors together, and we also talked about multiplying a vector times a scalar. So if we had a scalar alpha multiplied times the vector x, y, z, we just multiplied each component by alpha to produce alpha x, alpha y, alpha z, another vector. In this video, we're going to address the question, can we multiply two vectors? And the short answer is yes. There are two ways to do that. We can get a dot product where we take a vector, dotted another vector, and we produce a scalar, a real number. The other method of multiplying two vectors together is called a cross product, where we take a vector in Rn, cross it with another vector in Rn, and produce a vector in Rn. So two different ways of multiplying a vector with two very different types of results, one a scalar and one another vector. Here is the overview slide of what we will cover in this video. First, we will define, given two vectors, the dot product of these two vectors with two different notations. You can either use the dot or you can use this bracket notation, is equal to the sum of the component by component multiplication. So you can look at the definition here. And the note that we want to keep in mind is that the inner product, or this dot product, takes two vectors and produces a scalar. It's important to remember that the dot product produces a scalar. Literally, if you get confused on that, you don't know what space you're in. And I will tell you what space you're in. With the dot product, you're producing a scalar. So you are in the real numbers, you're in the space of R1. The next thing we'll talk about are properties of an inner product. The dot product is an example of an inner product. So we'll look at the properties of the inner product, which include one, that the dot product is always positive and only equal to 0 if your vector is equal to 0. Two, if you take this alpha is a scalar. If you take alpha times a and dot it with b, that's equal to alpha times a dot b. And something similar if you multiply b times a scalar beta. You have sort of this distributive property over addition of a dot b plus c is equal to a dot b plus a dot c. And then last you have a dot b is equal to b dot a. You have this commutative property. We will define the norm of a, which I often call the absolute value because it's notated like the absolute value and actually has the same sort of connotation. So the norm of a is equal to the square root of a dot a. And from the Pythagorean theorem, we'll see that the norm of a is the length of the vector a. Next, we'll look at the geometric interpretation of the dot product, which is just as important as the algebraic interpretation. So you want to be familiar both with this algebraic definition as well as this geometric interpretation. So u dot v is equal to the magnitude of u times the magnitude, I should say the norm of u times the norm of v times cosine theta. So what you can see is this dot product gives you information about the angle theta, which is the smaller angle between u and v. And then we have the super important corollary. And I call it super important because often people think corollary is just sort of like this little result that isn't that important, but this one is. So if the dot product of two vectors is 0, what that means is this cosine theta is 0, which means they are orthogonal. Last, not quite last. We'll look at dot product and projections. So this is one of the applications of the dot product. And last, we'll look at the equation of a plane normal to a vector. So a plane that's perpendicular to a vector containing a particular point x naught, y naught, z naught. And here is the equation of the plane written in terms of your vector, your normal vector, and your point. But I will also say this equation, it's really important that you understand how it's derived. And it's derived, as you may have guessed, using the dot product. And the reason why it's important to know how this is derived is you'll have many other questions, or it's typical, you'll get an exam question on something that uses the same ideas as how this equation is derived. So it's important to understand the ideas behind the derivation of this equation. So now that I've given you a quick overview, we'll go through each topic in detail with more examples. We'll start with the definition of the dot product. So if we have a vector u with components u1, u2, u3, and a vector v with components v1, v2, v3, then the dot product is simply the sum of the component-component multiplication. In other words, u1 times v1 plus u2 times v2 plus u3 times v3. And sometimes we have this alternate notation, which is this bracket notation, which is easy to type. But more often than not, we'll have this dot notation, which is this bold kind of dot multiplication sign. And I cannot emphasize this enough. It is important that you know that a dot product takes two vectors and produces a scalar. Because if you're confused about this, you literally don't even know what space you're in. So look at this definition and see that a dot product of two vectors, here you need to convince yourself that once you multiply the components and then sum them together, you will get a scalar. While there is nothing wrong with being lost, I assume you're taking a course in vector calc, and at some point you'll need to convince someone like your professor or grader that you know your way around. These are the properties of an inner product, and again, the dot product is an example of an inner product. So first, when you dot a vector with itself, it's always greater than or equal to 0. Dot products are always positive, and the dot product of a vector with itself is only equal to 0 if and only if that vector is equal to 0. Second, if you have a scalar times a vector and then you dot it with another vector, that you can pull out the scalar and you can dot the two vectors together first and then multiply by a scalar. And here the second point is that it doesn't matter if the scalar is multiplied by the first vector or the second vector, you can pull the scalar out. We have this kind of distributive property, so a dot b plus c is equal to a dot b plus a dot c. And then we also have this commutative property, a dot b is equal to b dot a. The proof of these properties, since the dot product relies on the addition and multiplication of scalars, at this point, right, u1, v1, these components are just real numbers. So the proof is going to rely on the properties of multiplication and then addition of real numbers or scalars. And so the proofs are fairly straightforward, but we'll do one just to say that we did. We will do the proof of this third property here. A dot b plus c is equal to a dot b plus a dot c. And we'll start by letting a equal a1, a2, a3, b equals b1, b2, b3, and c equals c1, c2, c3. And to prove any of these, this is in general, but I'll show you with this one example, what we are going to be doing is using the properties or the definitions of addition and multiplication and try to break things down till we just have real numbers. Like here, we only have real numbers, and then we can use the properties of scalar multiplication and addition, move things around till we get back to the form that we want. So I have my a dot b plus c is equal to, and now I'm going to use the definition of b plus c. So that's a dot b1 plus c1, b2 plus c2, and b3 plus c3. Now using the definition of this dot product, we're going to have, this is a1 times our b1 plus c1, a2 times our second component, and then our third component of a3 times the third component of this b plus c vector. Now at this point, our a1, b1, and c1, all of these are now just real numbers. They're scalars. So we can use the distributive property of addition, multiplication of real numbers to kind of rearrange, well, one, to multiply the a1 in. So we have a1 plus b1 plus a1 c1, a2 b2, a2 c2, and a3 b3, this should be a plus a3 c3. Once we have this all broken up, now we can build back up so it looks something like this. Looking at the form we want AB grouped together and AC grouped together. So that's exactly what I did. I took my ABs, these are our first term of each of the components, and I grouped them together, A1, B1, A2, B2, A3, B3, and then I took my second terms with the AC components. So I grouped those together, A1, C1, A2, C2, and A3, C3, and then by the definition of addition of two vectors, I can break this up as this vector plus this second vector here. So the AB vector plus the AC vector. So you can look at this, compare it with the addition. And then last, once I have this A1, B1, A2, B2, A3, B3, that's just A dot B. And this over here is just A dot C. So this is my proof. I've concluded what I wanted to prove. Next, we have the definition of the norm of A, which we denote with these symbols that look like absolute value for reasons which will become apparent later, and that's equal to the square root of A dot A. In fact, we are going to get to this norm being the length right now. So if we look at A dot A, we can write out our A as A1, A2, A3, and I always use A3 as my example. This can be generalized to AN, except that 3 dimensions is the most I can draw. So we're going to do it with 3. And also, I can't keep going on to n. So A1 times A1 will give me A1 squared, A2 times A2 gives me A2 squared, and A3 times A3 gives me A3 squared. When I take the square root of then A dot A, I get the square root of A1 squared plus A2 squared plus A3 squared, which is the length of A by the Pythagorean theorem. So that is what I have noted here. A quick example. So if A is equal to 4, 3, then the norm of 4, 3 is equal to the square root of 4, 3 dot 4, 3, which is the square root of 4 times 4, plus 9 times 9, which is equal to 5. Continue with these ideas. Vectors with normal 1, in other words, with norm equal to 1, are called unit vectors. They have a unit length of 1. And A over the norm of A is the unit vector with direction A. And sometimes we note that with e to the A, e underscore A, e of A, which I never use this notation, or very rarely, I should say. So the idea is sometimes we want to know what direction this vector A points in, and we're going to use the direction of A, but we really don't want the magnitude of A. So what we do is we take A and then we divide by the norm of A. So here, A divided by norm of A would be 1/5, because that's the length of our vector, times our vector 4, 3. Again, this gives us a vector in the direction of A, but with unit length, or length 1. And this really isn't superfluous. I used to think that, I don't know why math teachers wanted to make me normalize things. After all, you already have the vector. The direction's already kind of baked in. But the idea is later in physics or other kind of applications, you really are interested in moving something a certain direction, but you don't want to impact its length, or if it's a velocity sort of thing, you don't want to impact its speed. So you really need to isolate just the direction. Last point for this topic is the distance between 2 points B and A is the norm of B minus A. This next topic is the geometric interpretation of the dot product. And of course, the algebraic interpretation is important because that's how you're going to get answers to problems. But the geometric interpretation is equally important. It's not one of those things that's nice to visualize if you can. It's really important because this geometric interpretation, it's going to allow you to do things like get equations of tangent planes, which is sort of like in first year calculus, you learn how to get the tangent line, which was like the derivative, so it was super important of everything. This is the equivalent. Tangent planes is the equivalent of a tangent line. And so, this is one of the things that's going to help you. There are many other things that the geometric interpretation is going to help you apply different things to different types of problems. I'm going to clear out some of this stuff and move some things up so there's a little more space for us. The first thing I'm going to do is rewrite this definition of the dot product right over here. So u dot v is equal to the norm of u times norm of v times cosine theta, where theta is the angle between your two vectors u and v. And also, since I deleted the information about the norm, I just repeated the definition here for your reference. So the norm of A is equal to the square root of A dot A. Looking at this definition of u dot v, we have the algebraic definition here. We can calculate this here. We can calculate the norm of u and we can calculate the norm of v. So this dot product, this geometric interpretation, gives us information about theta. In other words, I can solve for cosine of theta. So I have u dot v over norm of u, norm of v, which means I can then solve for theta, which will be equal to the inverse cosine of u dot v over magnitude of u, magnitude of v. As you can see, by looking at this geometric interpretation of the dot product, we now can find the angle between two vectors u and v using the dot product. Now we are to our super important corollary. If the dot product of two non-zero vectors is 0, they are orthogonal. So let's take a look at our formula for the dot product. So if the dot product is equal to 0 and u is not equal to 0 and v is not equal to 0, they're not going to have a non-zero length, which must mean that cosine of theta is equal to 0. And what that will imply is that theta is equal to 90 degrees, or 90 degrees plus some multiple of 360. But we'll simplify that and say it's equal to 90 degrees, so they are orthogonal. So this geometric interpretation is exactly how you're going to find orthogonal vectors. One of the important applications of the dot product are projections. If you have two vectors A and B, the vectors A and B will define a plane. If you have a vector C that is in the plane spanned by the vectors A and B, so it's really convenient if you've had linear algebra, but that's okay if you haven't. So if C is in the plane that A and B defined, then the projection of C on A is the component of A that contributes to the vector C. Another way of thinking of this, you can think of this part, the component of A, as the shadow that C would cast on A. I moved my diagram up here to give me more space, also to make it a little bigger, and I took the plane that A, B, and C are in, and I drew just that plane so I can look more easily at this in 2 dimensions. So I have my vector A here, my vector B here, and then my vector C. And this might remind you, these projections might remind you of physics when you used to decompose a vector into a x component and a y component. And this is very similar, actually. It's really just the same, except that B is not perpendicular to A, or not necessarily perpendicular to A, like the x and y axis are in the xy coordinate plane. But the idea is the same. If I want to look for the length of this component of C on A, or the projection of C on A, and again, I'm only looking for the length, I'm not adding the direction of the vector, I can notice that the angle between C and A, the cosine of that angle, is equal to my alpha prime over the length of C. Solving for alpha prime, I get alpha prime is equal to cosine of theta times the length of C. But I also know from my inner product that A dot C is equal to the length of A, the length of C times cosine of theta. So I can replace this cosine of theta with A dot C divided by length of A, length of C, and that's what I have done here. So this cosine is replaced by A dot C divided by the norms of the 2 vectors. So now I have that the C's cancel out. I have A alpha prime is equal to A dot C over the magnitude of A. If I now want to add the direction onto my projection, because currently I only have the length, this alpha prime is only the length from the origin to here. If I want to add the direction, I can multiply my alpha prime by A, and that will give me the direction of A. But then I also need to divide by the length of A so that I don't disturb this length that I found here. And this last very important application, you'll be seeing this a lot because it talks about finding the equation of a plane. You know how in one-dimensional calculus you were finding the tangent line? Well, here you'll be finding tangent planes. So you need to be familiar with the equation of a plane. So the equation of a plane, so I've drawn this plane, shaded it in yellow. Normal to a vector n equals ABC. So this vector n, which I just labeled n, I didn't put ABC, but we'll use ABC later. This vector n then is at a 90-degree angle to this plane, and that's what it means to be normal to the plane. And it contains the point x naught, y naught, z naught. So I drew the point x naught, y naught, z naught. And also you see that my normal vector is the head of my normal vector is at x naught, y naught, z naught. But really, there's a normal vector here. This vector is also 90 degrees. There are lots of normal vectors. So I just happen to choose to illustrate it this way. But here we have a normal vector. We have a point on the plane. This here gives you the equation of the plane. So in other words, any point x, y, z on the plane will satisfy this equation. That is a times, and that is from our normal vector, times our point x minus x naught. X naught is a point on the plane, plus b from our normal vector times y naught. That is the given vector on the plane, plus c, again from the normal vector, times z minus z naught. That's the point given on the plane. Any point x, y, z that satisfy this equation is on the plane. For that reason, we say that this is the equation of the plane. This equation, it's a really convenient equation to have memorized because sometime later you'll see that you'll be given this equation and you'll want a normal vector, so it's really easy to be able to pick it out. That's A, B, and C. Sometimes they don't even tell you this equation is a plane. It's up to you to recognize it because there's nothing with powers of 2 or anything like that. So you have A, B, C. You can say, oh, there's my normal. But I would say even more importantly than remembering this equation is to know how to derive this equation, which we will do in just a minute. The derivation is almost a basic skill. The steps, the thinking you take to do it, the tools you use to do that is something that is just going to be basic, and it's going to be the start of many problems that you will almost certainly see in your homework and just as certain to see on an exam. And also, even just on the next chapter when we talk about cross products, we'll be using this equation, kind of the techniques we use to get this equation to develop some other things as well. So really important that you pay attention to the derivation. To develop this formula, I'm going to start by considering a representative point on the plane xyz. And I'm also going to enlarge my picture, and here's my point xyz. Again, this is just some representative point. I could have drawn it anywhere, but I chose to draw it here. And this, again, is the point, kind of the representative point x, y, and z. The line joining the points x naught, y naught, z naught, the point that we're given that's in the plane, and x, y, z, our representative point, must also be on the plane since both points are on the plane. I've reminded you the equation of a line from A to B. We had talked about this when we were talking about subtracting two vectors in one of my first videos. So the equation of a line from A to B is equal to B minus A, and there is a direction associated with this. This goes from the direction from A to B in this arrow. To the point in our example, the line, or x, y, z minus x naught, y naught, z naught, is the line from x naught, y naught, z naught to x, y, z. And again, because these 2 points are both in the plane, that means that this vector is also in the plane. Since now the plane and also the lines right on the plane is perpendicular to our normal, when we take this vector in the plane, which is x minus x naught, y minus y naught, z minus z naught, dot our normal vector ABC, I can't find our normal vector here, ABC, it'll be equal to 0 because they're normal, and by our very important corollary, that means their dot product is equal to 0. So ABC dot this vector here gives us A x minus x naught plus B y minus y naught plus C z minus z naught is equal to 0. And that is exactly the equation we have here. And there is a warning I have to give to you. So one thing you might be tempted to think is x naught, y naught, z naught was given to you, and if you dot it with the normal, then it would equal 0, and that would be wrong. In general, this is not true. And the reason why is this x naught, y naught, z naught, it is not a vector in the plane. It is a point on the plane. And in particular, this is the vector. It is that x naught, y naught, z naught is the n-coordinate of the vector. So this vector here that goes up and ends on the plane, it is not necessarily perpendicular to n. For this reason, we couldn't just dot x naught, y naught, z naught, with n. What we had to do is we had to take a representative point on the plane to create a vector in the plane. And then we can dot it with the normal and say it is equal to 0. Now that we've covered the main ideas, I have 5 examples to go through with you. So the first thing we get is the Cauchy-Schwarz inequality that says the magnitude of A dot B, and again remember this dot product produces a scalar, so the magnitude of A dot B is going to be less than or equal to the magnitude of A, magnitude of B, cosine of theta. And this inequality holds directly because of the definition of A dot B, and here I have the definition of A dot B. And what you want to note is cosine of theta is equal to 1 when theta is equal to 0. So if A is not collinear with B, then cosine theta is going to be something between 0 and 1, but definitely less than 1 if they're collinear. And in other words, the angle between them is 0. So then the Cauchy-Schwarz inequality will hold. My next example, find the angle between the vectors I plus j plus k and I plus j minus k. First, I'm going to rewrite the vectors as 1, 1, 1 and 1, 1, negative 1. Then next, I'm going to use my dot product. So 1, 1, 1 dot 1, 1, negative 1. And using my theorem, that's going to equal to the length of 1, the length of 1, 1, negative 1, times cosine of the angle between the two vectors. And again, this theta is what we're trying to look for. So this dot product is 1 times 1, which is 1, plus 1 times 1, which is 1, 1 times negative 1, which is minus 1, and that's equal to, and again, the length of this is square root of 3 times square root of 3. And I've taken this calculation for the length off to the side just as an example. And then, so I have square root of 3, cosine of theta. So that means the cosine of theta is equal to 1 over 3. Plugging that into the calculator, that says theta is 1.23 radians, or 71 degrees, approximately 71 degrees. My next example, prove the vectors cosine theta, sine theta 1, and negative sine theta, cosine theta 0 are orthogonal. So I'm going to take the dot product of those two vectors, and remember, if the dot product is equal to 0, where is this, then they are orthogonal. So if I could show the dot product 0, then I'm done. And here I did the dot product, and you can see my sum is equal to 0. So by my corollary over here, I have shown that the two vectors are orthogonal. The last example problem deals with projections, which I have our notes over here. So let A and B be two non-zero orthogonal vectors. If C is a vector in the plane spanned by A and B, so C is in the same plane as A and B, then there exist scalars alpha and beta such that C is equal to alpha A plus beta B. If you've had linear algebra, it's just saying that C is a linear combination of A and B. Use the inner product to determine alpha and beta. So we're going to start by taking the inner product of A and C. So we have A dot, and then C, we're assuming we can write it as alpha A plus beta B. And we're assuming that's true because this example told us that we could. There exist scalars, alpha and beta, such that C is equal to alpha A plus beta B. So here I've performed my dot product, and I moved my terms around because I can, because of the properties of dot product, I can pull out scalars. So I have alpha A dot A plus beta A dot B. So I have alpha A dot A, and then what I know about A dot B is that it's equal to 0, and it's equal to 0 because A and B are perpendicular. So then it's just algebra that I can solve for alpha. It's equal to A dot C over A dot A, it's also written in this form. So this is quite straightforward from the definition, and if you understand that A dot B, because they're perpendicular, equals 0, it's very straightforward from the definition and algebra. Reviewing what we have covered in this video, we talked about the dot product, and the first thing we did is we defined the dot product between two vectors of u and v as the sum of the product of the individual components, u1, v1 plus u2, v2 plus u3, v3. And we especially wanted to note and remember that the inner product, or this dot product, takes two vectors and produces a scalar. We looked at properties of an inner product, and a dot product is an example of an inner product, so it also has these properties. One, the dot product is always positive, and it's equal to 0 if and only if the vector itself is equal to 0. Two, if we multiply a vector by a scalar and then take a dot product with another vector, then we can pull out the scalar and then do the dot product first and then multiply by the scalar. We have this distribution, so if we have a vector A dot vector B plus vector C, then we can do A dot B plus A dot C. And also we have this commutativity, so A dot B is equal to B dot A. We define the norm of A that is notated with these symbols that look like magnitude or length of A is equal to square root of A dot A. And we expanded this out, A dot A, and found that it was essentially this form here, which is a1 squared, in R3 would be a1 squared plus a2 squared plus a3 squared, all square rooted. So by the Pythagorean theorem, we said that this is equal to the length of vector A. So the norm is equal to the length, hence that notation that looks like length. Vectors with normal 1 or vectors with length of 1 are called unit vectors. And A over the norm of A is the unit vector with the direction of A. So when we need to isolate a vector's direction, then we have A over length of A. And we saw that in projections, we wanted to have the direction of a vector, but we didn't want the magnitude or the length to interfere with the magnitude of the projection. So we wanted to isolate just the direction, and that's exactly what this unit vector does. Also, the distance between 2 points B and A is magnitude of B minus A. Just as important as this algebraic definition was the geometric interpretation of the dot product. So U dot V is equal to the magnitude of U times the magnitude of V times cosine theta. And I guess I should say norm of U, norm of V times cosine theta. So what that tells us is algebraically we can figure out this U dot V. We can solve, and we also know how to calculate norm of U and norm of V. So we can solve for cosine of theta, and therefore we can solve for theta using the dot product. And then we have this super important corollary that the dot product of two non-zero vectors is 0, because if the dot product is 0, and if the vectors are non-zero, so in other words, the norm of U and norm of V is not equal to 0, that must mean cosine of theta is equal to 0, and that happens when theta is equal to 90 degrees, which means the vectors are orthogonal. We used the dot product and we found the projection. We talked about the projection, which is an application of the dot product. And then we also looked at the equation of a plane, normal to a vector n. So here's my plane in yellow. N is my normal vector. It's perpendicular to the plane. So the normal gives you a direction perpendicular to the plane, and it contains the point x naught, y naught, z naught. We found the equation of the plane is equal to a x minus x naught plus b y minus y naught plus c z minus z naught. So our a, b, c, we can read that off as our normal vector. And then our x naught, y naught, z naught is given to us. So this here, this formula is important to remember because in harder problems, you'll get an equation and you'll want a direction. And the normal is something you can read off immediately. Later we'll see with cross product, then you can find things that are parallel, not just normal. But we start with a normal. So that's important. It gives us a direction. But just as important as this formula will be how we derive the formula, because the techniques we use, the ideas we used are helpful. One, when we do cross products and certain applications of cross products, and I can't remember the application, but we'll get to that. And then the second thing is lots of examples that you'll see in your homework and almost certainly on any exam you take. So it's important to understand how this formula was derived. Finally, for review, I have these 5 problems for you to try. So the first one is to calculate 120.111. The second is find the angle between these two vectors, 120 and 111. The third is to find the distance between 120 and 111. The fourth is to find two non-parallel vectors, both orthogonal to 1, 1, 1. And last, find the projection of 2, 1, negative 3 onto negative 1, 1, 1. I suggest you pause the video, give them a try, and when you come back, I will have solutions to these problems. Here are the solutions to the 5 review problems. In the next video, we'll talk about the cross product, which is the other way of multiplying two vectors. But that's it for this video. Thank you for watching.